from electrical machine 1. So, these are my content of today's lecture. It is I have taken from module 1 single phase transformer. So, in this today's lecture I am discuss about the ideal transformer, and in the ideal transformer what assumptions we are going to take, then phasor diagram of ideal transformer at no load and at load condition. Then we will discuss the practical transformer at no load and at load, at leading load and the lagging load. So, we will start with the transformer. As you everybody like knows about the transformer. Transformer is a static device which transform the transfer the electrical energy from one electrical circuit to the another electrical circuit through a medium of magnetic field without changing the frequency. So, it is basically principle behind this transformer is the electromagnetic mutual induction. It mainly changes the level of voltage and current from high to low or low to high. So, before start with this transformer basics, you must know about the application of the transformer. So, there are some of the application of transformer. These are the application. Basically, transformer is used to change the level of voltage and current from one circuit to the another circuit. So, basically it is used in the power transmission lines at the receiving end and at the sending end also. Second application we can use it is an impedance matching for maximum power transfer in the electronic circuit, where the transformer low rating transformer has been used. And third, it can be used for the isolation purpose, because here we are going to discuss the two winding transformer. So, when we transfer from electrical energy from one circuit to the another circuit, it is transfer from the magnetic circuit medium. And now we will start with the ideal transformer. So, ideal transformer, we have taken some assumptions for the ideal transformer. First is the winding resistance, we have to take a 0, and second is the no leakage flux will be there. The magnetizing current is very small and there is a no core losses. Now, we will start with the basic EMF equation of the transformer. Here you can see that if you see the here just I have taken the two winding transformer. This is the load and this is supply is given. So, this is the voltage input single phase supply. So, as according to the principle of transformer, as we apply the voltage, the input voltage here, the current will start flowing, that is called the no load current. Suppose the switch S1 is S1 S2 is open here, and when the voltage is applied here, the current will start flowing, right. So, as the current will start flowing, this voltage will set up, because it has the core, so it will set up the flux. Suppose the phi flux will be set up here, and this flux is linked with the other winding with the help of this core. So, this flux, the nature of the flux will be the nature of this flux is the changing flux. So, according to the EMF, according to the Faraday's law, this changing EMF will induce an EMF. So, here you can write E is equal to minus N d phi by dt. Here I am just drawing again the diagram so that you can understand it better. Here you apply the AC supply, the no load current start will flowing here, and the flux will be set up, suppose phi. This has the number of turn N1 and this is the number of turn N2. So, suppose phi is the taking as a flux as the reference. So phi can be expressed in terms of phi m sin omega t, right? So due to this voltage, because voltage is sinusoidal, so pulsating voltage is there. So due to this voltage, pulsating flux will be produced, and suppose this flux will be taken as phi m sin omega t. So due to this flux, changing flux, the EMF will be induced according to the Faraday's law, and it can be written as E is equal to minus n d phi by dt according to the Faraday's law. Now this phi value can put in equation 1, so E can be expressed minus n1 d by dt phi m sin omega t, right? So this can be written again minus n1 phi m cos omega t. Again it can be written as minus n1 phi m sin omega t minus pi by 2. Right. So this EMF is induced in the, suppose N1 is the high voltage side and this is N2 is the low voltage side. So this E1 will be produced in the high voltage side, and it is the instantaneous value. Right. So this is the instantaneous value, and so this can be treated as a maximum value, a minus n1. This is omega also here. So minus n1 omega m phi m omega is treated as a maximum value. So it can be written as E1 max n omega phi m, and this can be represented by 2 pi f. Omega can be replaced by 2 pi m, and this is the maximum value, right? So RMS value will be maximum value divided by the root 2. So it can be expressed 2 pi f root 2 n phi m. So it can be written as 4.44. If you solve this 2 pi by root 2, it can be 4.44 f phi n1 in the primary. So it is E1, this RMS value, this is the RMS value. So according to the when we apply the voltage in the high voltage side, you will see that the EMF will be induced here, and the RMS value of EMF can be derived, and it can be written as 4.44 f phi n1, right? Now similarly, because in this circuit you can see here E1, due to the transformer action, this flux will be linked with the, we assume in the you can see in the ideal, because now we are discussing the ideal transformer. So in this we have seen that the no leakage flux will be there. So I have assumed that the all flux which is produced by the primary link with the secondary, all flux will be confined in the core only, no flux will be leaking in the air, right? So according to that, this same flux will be linked with the low voltage side or the secondary side, and this is also the nature of this flux will be is the changing. So this is also responsible to produce the EMF in the secondary side in a similar manner. So E2 can be written as, the E2 RMS value can be written as 4.44 f phi n2. So it can be written E1 by E2 is equal to, if you divide equation 1 and 2, this is equation 2, n1 by n2. So the voltage can be transferred from one electrical circuit to the another electrical circuit in in the form of transformer ratio, the turned ratio, right. So, now I am going to develop the phasor diagram at no load. So, here you are seeing that the voltage will be the generated voltage at the transformer at the high voltage side and the low voltage side will be expressed in this way, right. Now, we are trying to and one observation also you can see, we have taken the phi, the reference is the flux phi, and when we derive through this, we are seeing that the phi, the EMF induced by this flux is phi m, this sin omega t minus pi by 2. That means the voltage induced in the primary as well as the secondary, it is 90 degree lagging with the flux phi, right. So, now we will try to develop the phasor diagram at no load. So, I have just taken the flux, the reference flux taken as a reference voltage, and in this case, in the previous case we have seen the flux will be phi m sin omega t, and the voltage induced by this flux is 90 degree lagging with this voltage with this flux, because in this expression sin omega t minus pi by 2. So, it can be drawn here, this suppose this is E2, this is E1, the length of the phasor depend upon the length of the, if N1 is greater than N2, so E2 must be, sorry, E1 is greater than E2, right. Now, in this case you can see here E1 is developed, here E2 is developed, and this the voltage V is applied here. So, according to the KCL, this plus polarity, this is minus, so E will be, V is equal to, V will be your minus E1. So, in phasor diagram, this V you can draw here, right. Now, because one thing also you can see here, like in this case you assume that in there is no winding resistance, so you haven't include any winding resistance in the phasor diagram. There is no leakage reactance, that means you are assume all the flux is confined within the core, there is no core losses, and the magnetizing current is very small. The concept of magnetizing current is, it is used to produce the flux, right. It is responsible to produce the flux actually. So, in this case you can see that Im is always same phase with the flux, right. Because if you see in this equation, E is equal to 4.44 F phi n. So, in this equation you can see phi is equal to your E by 4.44 F phi n, F phi n. Right. So, in this case, if your, and this E is equal to your V, so 4.44 F phi n, Fn, right. So, in this case you can see voltage is constant and the frequency is also constant, your input voltage is and the frequency is constant, so your phi remains constant in the core. So, to produce that much amount of flux, you need some magnetizing current. If you have the if your material is is have lower permeability. अगर material की आपकी if you have the permeability lower, so you need large amount of magnetizing current to set up that much amount of flux. So in this case, ideal case, you assume that the permeability of the material is tends to infinite. So that means very less amount of magnetizing current is required to produce that constant amount of flux. So the concept of magnetizing current is that only, right? So we just draw a very small phasor in the direction of flux, because this current is only responsible to produce that much amount of flux. So this is the phasor diagram of the transformer at the ideal transformer at no load. Now we are trying to develop the phasor diagram of the ideal transformer at load condition, right? So I am just I have connected the load here. Here the supply will be there. This is V. This is switch S1, S2, and here the E1 is developed, here E2 is developed. Because here you assume the winding resistance is 0, that's why we assume here V is equal to your minus E1. Otherwise their drop will be there due to the winding resistance, right? Now we are trying to develop the phasor diagram at load condition, at lagging load condition for the ideal transformer. So suppose this load will be lagging. Now first just draw the flux, the reference I have taken flux, then due to this flux E1 will be induced. So this E1 will be lagging behind the flux by 90 degree. And the length of the phasor of E1 into will be depend upon the turn ratio, right? Now in this case I have taken N1 will be greater than N2, right? So this is E2 and this is E1. Now Im will be there, this is Im, and the voltage is there, right? Because this E1 must be equal to your V1. You apply the KCL here, so this will V1 will be equal to V1 will be equal to your minus E1, right? Now when we switch on this transformer, this load must be connected with the secondary of the transformer. Now this current will start flowing, the I2 current, the load current will start flowing, right? So when we loaded the transformer with the lagging load, suppose this is the R plus Jx or Z, this is lagging load, so the I2 will start flowing. Now just listen carefully, when the I2 will start flowing, this will produce its own MMF because of the number of turns will be there, so it will produce the MMF N2 I2, right? And previously I said that when the as you apply the voltage in the secondary side, as you apply the voltage in the primary side at a constant voltage and frequency is constant, so your flux setup in the core will be constant, right? Now if you connect the load, the I2 will start flowing, and due to this I2 the MMF N2 I2 will produced, right? But in this case you see that in the core the flux is constant, so the flux which is produced by this MMF must be nullified, right? Because suppose N2 I2 will produce the flux phi 2, So that flux must be nullified, because in the core the constant flux will be there. Constant flux will be there because the voltage and frequency is constant. So the core must contain only this amount of flux. So whenever the load is, this is called the loading effect, when the load is connected in the transformer, the I2 will start flowing. Due to this I2, N2 I2 MMF will be produced, and this N2 I2 MMF will be nullified by the some other means, right. So because this N2 I2 will produce the flux phi 2. So now as the load is connected, in the primary side, the another current, that is I1 dash will be flow, which is equal to the I2. Same current I1 dash will start flowing, and this I1 dash multiplied by N1 will produce its MMF, which nullify the effect of the load. So thus this transformer will contain the flux, only flux phi. Okay. Now in the previous you said, you see that at the no load condition, the primary carry only the no load current, right, that is the magnetizing current, right. Now as we connect the load, the I2 will start flowing, and due to I2 N2 I2 MMF will be produced. MMF will produced in the low voltage side, you can say, right. So that amount of MMF will produce the flux phi 2, right. So this flux phi 2 must be nullified. That's why the I1 dash current will start flowing in the primary side or high voltage side, right. Now you can see, now this in the primary side, two current, primary or the high voltage side, two currents are carried. One is the magnetizing current, that is no load current, you can say. The second is the I1 dash current, right, which must be equal to the I2, right. So that in the primary side, MMF in the primary side will be I1 dash plus IE multiplied by N1, and MMF in the secondary side I2 N2, right. So if you so total MMF present in the transformer must be IE N1 or IMN1, you can say IMN1, right. So I1 dash N1 must be equal and opposite to I2 N2, so that the flux phi m only sustain in the transformer. So in this case you can see that now we will try to develop the phasor diagram at lagging load. So here we can see that as the switch is off, switch is on, the I2 will start flowing. Suppose it is a lagging load, so suppose that this is the voltage V2. Voltage V2 is here. So V2 will be here, and the I2 is lagging, right. Suppose the theta will be the load power factor is suppose theta 2. So this is V2, because I have taken, because there is no drop between the V2 and V2. So we will assume that this is equal, right. Now whenever load is connected in the primary, the equal amount of current will flow, which is same as I2, right. Equal and opposite amount of current will start flowing. So it can be represented in the phasor diagram. This is I1 dash, which is equal to your I2, right. So total current, if you add both the phasor, the I1 dash and IM, you will get the total current, that is I1. So this is I1, which is the current which is flowing in the primary side, which is the phasor sum of the magnetizing current as well as the load component. This is also called the load component, right. So this is how we can able to draw the ideal transformer, phasor diagram of ideal transformer at lagging load. Now we will see that if the load is leading, that means it is a, if it is a capacitive load, how we will able to draw the. So now if the transformer is ideal load, so just draw first, this for practice purpose, you can try even. So this is flux phi, and E1 will be produced here, and this is E2. Now here we will connect the leading load, the capacitive load. This is V. So E1, E2, this is your magnetizing current, which is in same phase with the flux, and now when switch will be on, the I2 will start flowing, and due to this I2, the I1 must be flow in the I1 dash must be flow in the primary side, which is equal and opposite to I2, so that this will confine with the flux, constant flux only, because constant flux, why it is called a constant flux, because V is equal to 4.44 F phi N. So N is the constant number of turns for the particular transformer is constant. If you apply the constant voltage at a constant frequency, the flux remains constant. So this has to be the constant amount of flux has to be there in the transformer. So whenever I2 will start flowing, equal amount of current will be flow there, so that it the effect of I2, due to I2 how much amount of like N2 I2 the MF will be produced, that must be nullified by this I1 dash current, right. So that this transformer will confine only the constant amount of flux. Okay. So now this is V1, this is V1 applied voltage here. Now V2 is there, and I2 is, sorry, it's for leading. So it's for leading. So the current will be like here. Leading means the current is lead with the voltage by some angle, right. So according to this I2, the equal amount of current will start flowing, that is I1 dash, and now the phasor sum of I1 IM will be now I1. So in the primary the current will be I1 dash plus IM. So this is the phasor diagram of the ideal transformer at a leading power factor, right. Now we will start with the practical transformer. the in ideal transformer we have assumed so many assumptions, like we have neglected the winding resistance, and we have neglected the leakage flux, we have neglected the magnetizing current, and we have neglected also the core loss. Now we are trying to, because if you are making the model of the transformer, you have to make the add these you can say in practicality in the ideal transformers to make it a practical transformer, right. So one by one I am just inculcating or include the these things in the ideal transformer to make it a practical, right. So first I am just taking the effect of core loss or introduce core loss in the ideal transformer, right. So when we introduce the core loss in the ideal transformer, you just aware about the core loss. So core loss is due to the, I mean, if you see the core loss is the eddy current losses and the hysteresis losses. Eddy current losses can be minimized with the help of laminations, as you know, and the hysteresis losses can be minimized to use the high quality material, high conductivity material, high permeability material you can use to reduce the core losses, right. So if you see in this case how to introduce in the phasor diagram, like if you see the BH curve, just so I am drawing the BH curve of any material. This is BH curve, H or I, right, and this is suppose B or phi, right. So if you analyze this, you can see that this is suppose A point, this is B, this is C, and this is D, right. This is a A point. In this you can see this H or I is the same the magnetizing current you can see, and this B or this flux density, or you can say it is a flux. So in this you can see at point A the current is 0, the H or current is 0, but the flux is negative, right. At point B you can see the current is positive and your flux is negative, right. So if you draw the instantaneous value, with respect to omega t, and this is suppose current, magnetizing current. So this is suppose this is IE and this is suppose flux. So in this case you can see the current is leading with the flux. Here the current is, you can say here the magnetizing current is 0 at point A and the flux is negative, right. At this point you can see the magnetizing current is your magnetizing current is positive and your flux is 0. That means the current, the magnetizing current is leading with the flux. So that angle, and how much angle it will lead? Suppose it is called as a hysteresis angle. Right. So in this the observation will be the flux, the current is, the magnetizing current is actually leading with the flux, right, because of the this hysteresis loop. This hysteresis loop is the, when we magnetize the material and when we demagnetize the material, we will getting the hysteresis loop. So this will show the how the core loss will be, how the hysteresis loss will be there. So due to this hysteresis loss, there is a gap, the angle, the some angle gap between the flux and the current, right. If there is, so it depends upon the how much the hysteresis loss will be there. Like if the hysteresis loop will be a thinner one, it has the lower value of core losses or hysteresis losses. So, the total core losses will be reduced. So, due to this hysteresis loop, you can see the flux will be no longer in same phase with the current. It is now, the current is now leading with the flux due to this hysteresis. Now, we are trying to inculcate this concept into the phasor diagram. So, we will just introduce in this. Now, so here we can draw the phasor diagram, how we will inculcate the. So, here the flux will be there, right. If you draw the phasor diagram, flux will be there, and okay, I just cut this, I just take this page, using this page to draw the phasor diagram, right. So, how to inculcate this concept into the phasor diagram? This is flux, as you know, and what about the E1 and E2? The E1 is obviously lagging with the flux, right. So, E1 and E2 will be lagging with the flux by 90 degree, and at ideal transformer you have drawn IM in same phase with the flux, but due to the hysteresis loop, you can see, due to the hysteresis loop, the IE can be drawn leading with the flux. Now, it term as the exciting current, right. So, it has two part, one consider as one you can consider as this, the magnetizing current, and the other one you consider as this core loss component, right. So, IM is the, so now I can be written as the phasor sum of I IM, phasor sum of IM plus IC, right. So, this IM is, what about this IM? It is a magnetizing current, and this IC is the core loss component. So, this is the loss, this is the due to the hysteresis loss, right. And so, this current is responsible to produce the flux, only that much amount of current is used to produce the flux, that is called the magnetizing current, right. And this current will be the, you can say it is a core loss component, it is, this core loss will be due to the hysteresis, right, because this core loss, this IM or I is no longer in phase with in phase with the flux, right. Now, we are trying to see the second, we include the now winding resistance, second, now we include the because in this case you can see that in the practical transformer one we have seen that how we will inculcate, how we will see the effect of core loss in the transformer, right. Second, then we will include the winding resistance in the ideal transformer, because in previous we assume that the winding resistance is negligible, but In this case, you can see that we have to include the winding resistance, because winding resistance cannot be, in practical case winding resistance cannot be avoided, right. So, if you see here, this is a transformer. So, this winding resistance, this is V1, here the E1 will be induced, and this is the E2 will be induced, right. So, when here we consider the winding resistance, suppose R1, now the E1 is no longer equal to the E2, right. There is it creating some voltage drop here, so that the E1 will be now at no load condition. If you consider as a no load, suppose the the current will be there. So, V1 can be written as E1 plus IE R1. Now, we are not using the IM term. Here we can use the I, the exciting current term, which is the phasor sum of the magnetizing current as well as the core loss current, right. So, it can be written as this way. Now, we inculcate in this, include the winding resistance as well as we have to include the leakage reactance. Here you can see winding resistance, and the third we have to include the leakage flux, because we assume that the whatever flux is produced by the, you can see here also, whatever flux is produced by this primary, all flux will, we assume that all flux will link with the secondary, but it is not, practically it is not possible, right. Some of the flux is only linked with the primary and some of the flux is linked with the only secondary, and that flux is only confined in the arrow. So, leakage flux can be defined. Now, we introduce the effect of leakage flux. So, leakage flux, so अगर इस केस में देखें, so leakage flux is confined within the air second, it is only linked with primary or high voltage side, you can say primary only or secondary only, right. So, this is suppose phi L1 term as a phi L1, this is leakage flux. In the secondary side, it is considered as suppose phi L2. So, these leakage flux is not responsible to produce the main flux, I mean the voltage here. So, these are the, these flux is, nature of this flux is the sinusoidal only. So, this is also, this flux is also induce an EMF. So, that will consider in terms of voltage drop in the windings. So, phi L1 is responsible to produce the voltage drop in the primary side, phi L2 is creating the voltage drop in the secondary side. So, this is how this will inculcate. So, using this things, we are trying to develop the phasor diagram in the next lecture, and we will start from here only. So, thank you all, thank you.